Just 3 o'clock, that's good. Okay, thank you, good afternoon. I would like to present you the Fuzion Intermediate Representation, which is the intermediate representation for a new language called Fuzion, which has the goal to be an IR that supports static analysis, in particular for safety-critical systems. And this is a work in progress presentation, so I will only have 15 minutes, so I'll go quickly through all of that, but I'll be around all through the conference, so you can talk to me more in detail. A quick overview of what I'm going to do with you here now is I will start with a very, very quick introduction into the Fuzion language, then tell you what I mean by safety-critical aspects, before I then dive into the Fuzion toolchain, in particular talk a bit about what static analysis we do, and then give you more details on what our intermediate representation looks like and end up with the status of the current project. And I'm from Tokiwa Software, a small startup company in Germany, and this is joint work with Michael Lill, my colleague there. So starting with the Fuzion language, a very, very quick intro with a small example here is the main idea behind Fuzion is to build everything in the language on a single concept, and that's the concept of a Fuzion feature. In the small sample code, you see everything that is purple is basically a Fuzion feature or a reference to a feature. And a feature is basically a generalization of something like a class, a method, a function, what you have in other languages. And a very important aspect of features is that they may be nested. Fuzion is statically typed, and it is polymorphic in several ways. It has tagged union types, it has parametric types, and it has an object-oriented style of inheritance with redefinition. And Fuzion is a functional language. It is pure and uses effects, algebraic effects, to model non-functional as impure aspects. Like in this example where IO out is an effect used by this small hello world example. Now, coming to safety-critical systems, and I start with a picture of a typical safety-critical system, which is a surgical microscope for brain and eye surgery. And I know from my previous life that these kinds of systems are actually developed with languages like Java that run the rather complex software on these systems. So that's where I see the need for actually higher level languages for safety-critical applications. So what do safety-critical systems typically have in common? What requirements do they have? Typically, there are fairly strict formal guidelines for the certification of safety-critical software. And there are different guidelines, different standards for different application areas like avionics, industrial applications, automotive, medical, and so on. And what these guidelines typically prescribe is a very rigorous development, and in particular, a verification and validation process. So you need very strict documentation and traceability to ensure that the application actually performs correctly. And not always, but often, safety-critical systems also require to be deterministic. So there must be worst-case execution times for all the operations. For memory management, for example, that means that you only have the option to use either real-time GC or static memory management. And you cannot use, or you have a lot of restrictions in the use of probabilistic algorithms like hash tables, where you cannot easily bound the execution time. And the idea behind the Fuzion intermediate representation is to have an intermediate representation that makes it easier to develop tools that help with the development, particularly with the verification and validation process of safety-critical software. So let me show you what our tool chain, and in particular the static analysis tools there, look like. This is a complete overview over our tool chain. It starts pretty standard with a front end that takes Fuzion source code and compiles them into Fuzion module files. And that does the standard things a compiler front-end does, checks for local correctness, type correctness, and so on, but also verifies things like supply chain security, that any modules we depend on actually fulfill what they promise. Then the middle end takes a set of Fuzion modules and compiles them into a Fuzion Intermediate Representation, which represents a whole closed application. So the main thing the middle end does is so-called monomorphization. So it replaces all parametric types by actual runtime types. It does things like dead code removal and some smaller optimizations. Now, on top of the Fuzion Intermediate Representation, we can run different analyzers, optimizers, and the purpose of these is to verify the correctness of the application, so to verify the absence of certain runtime errors, to maybe specialize the code for better performance, do things like escape analysis, that we can know where to place allocations, that we can have allocations statically on the stack, or automatic freeing of allocations, or as a fallback if everything else fails, to fall back to the garbage collector. And also have tools that help with instrumentation, with test generation for all the certification artifacts that we might need. And now the result of these different tools is again the Fuzion IR, which is then the input for different backends. And this is the backends that we currently support, which is a Java virtual machine backend where bytecode is generated, or C source code, or we have an interpreter as well. So now let me tell you very quickly about the details what the Fuzion IR looks like. Fuzion IR is basically a set of runtime features. A runtime feature is a feature like I've presented you in the beginning, but equipped with actual runtime types for all the type parameters that the features might have. And a feature could be one of 6 kinds. It could be a routine, which actually can run code. It could be abstract. It could be a field, a variable. It could be a choice. A choice is basically our union type. It could be an intrinsic, or it could be native. And 2 of these feature types actually define a type that could be the type of a field, which is a routine, which defines a product type, or a choice, which defines a sum type. Then all but the choice type are callable. So a choice cannot be called because the instance of a choice is created by an assignment. But only routines actually contain code, contain bytecode that can be executed. And I will quickly show you what the code in our intermediate representation looks like. The intermediate representation basically is using a stack machine. And there's a very small set of commands. It's only about 10 commands the intermediate code supports. And the most important one is a call, so a call to a feature. Then there's assignment of a value to a field. And there are operations to tag values, which is wrapping a value into a choice type, so creating a tagged union type value. And the counterpart to that is a match, which takes a tagged union type value and switches over the different instances that this might have. And actually, the match is the only control flow operation that we have in our intermediate code, very similar to the Smalltalk talk we heard this morning. We don't have any construct for loops. What we do for that is we use recursive calls and tail recursion optimization in the backends to manage, to model those. And then there are some more intermediate instructions that I don't explain here in detail. Now, since we have so few so few instructions, the whole complexity that we to run actual arithmetic and things like that, the intermediate representation uses intrinsics, so specific features that the backend or the analyzer knows how to implement to realize more specific features. So all the arithmetic, floating point, integer arithmetic is done via intrinsics, but also anything that affects the runtime system, so internal things related to effects are all done with intrinsics. And what that means is that any tools that run on the intermediate representation, depending on what they actually analyze, they could just ignore certain intrinsics if maybe the details of some floating point operations do not matter for a particular tool. Those can be just treated as opaque values, while those that are important for a particular analysis need to be implemented by the tool. So I'm coming to the end, the status of the project. Fuzion is, and the tool chain is still under development. The language specification reaches a more and more stable state. The base library is still a big construction site and work in progress. We have the current implementation has backends running on the JVM and a C backend using Clang then to generate code. And we have basic analysis tools available. We're starting this month as a partner in a larger European project called Green Code, where with about 25 European partners, many large industries, we are developing this further. And yeah, basically that is my presentation. You find all of our sources are available on GitHub, and you find lots of information on our website and on our social channels. If you have any questions, I will be happy to answer.
We have time for probably 2 questions.
So if you go back one slide, please. No, sorry, not that slide. One more. Well, the intrinsics. Okay, so just a question about intrinsics. So the idea behind the IR is to statically model and for safety critical systems. Now, for each of the intrinsics that you're adding here, is this within the IR, and how are you going to model that? So for each intrinsic for a particular machine, do you expect the features for that intrinsic to actually be fed into the IR? How do you model that in terms of timing, in terms of what its effects are? Does it have to be fed in, or are you abstracting that away in some way?
I'm actually, maybe I'm cheating a little, because basically the set of intrinsics could be considered basically also as a set of intermediate commands that we have there, but we treat them so differently. We treat them just as features that are marked as intrinsics. And depending on what you are you're interested in, you might need to consider them or you might not in your tools. So definitely if you do a static analysis to maybe determine the worst-case execution time of a certain operation, you need to consider all of them and know the runtime performance that the backends will actually then require for those. Yeah. Thank you.
Any other questions?
Thank you.